your drafters are using, and you have the confidence that says, I can go look that up. I learned what this does. I know exactly where I can find that particular piece that's broken and go replace it, right? That is sometimes what we need to do. But a lot more often, you need to be able to say, what is this system doing? And really, more or less, a relay is a relay. Even if it has some specific little differences, it's going to do about the same thing. So we can take an obnoxious drawing like this, we can make it a little simpler, right? So here we have a stop and a start. We've got an auto mode, right? We're going to have safety signal, a shutdown. And all of those terms are just a lot more intuitive. And then we've got our different gates. So we've got and not, and ors. And depending on what these do, we're like, okay. So if it is in auto mode, or we get the start push button, then we can continue down here, right? So it just makes it a little easier to look at what the overall system is doing, rather than memorizing a bunch of slightly different and very easily to confuse symbols that are showing us the same function, right? So there's three basic types. Have you guys all learned about and, or, and not gates? Okay, so this is review. We'll go pretty fast. They have two states, on and off. This can be referred to the output, right? Output would be an on, output would be an off signal, okay? You can also say your output is high or low, 1 or 0, true or false. On is the same as high, is the same as a 1, is the same as true. So if you see these symbols in a logic gate, they all mean the same thing. And then these are their opposites. Okay? The state of the gate, or the output that it gives, is determined by the status of the inputs to the gate, right? Each type of gate will respond differently to the various possible combinations of inputs. An AND gate provides an on output when all its inputs are on, and if any one input is off, the gate is off. Okay? Or it's on when any one or the other is on, and off only when all of its inputs are off. And the not is the reverse of the and, right? If the input is on, the output will be off, and so forth. Okay? All this is review so far? Okay. You can also combine some of these that are frequently used together, right? So an and a not gate is called a NAND gate. You guys went through all these? Okay. I won't read these again. If it is new information, there's the slide, but we'll jump forward. Okay. This truth table, have you guys done this before? Yeah? Okay. I'm going to go through it just real quick then. So with an AND gate, A and B gives Q, right? So A and B gives us the output. If A is true and B is true, then so is Q, right? So if you have the same input, your output will match the input. If either one does not match, if A is not 0 and 0, or it's not 1 and 1, your output is going to be off, right? Truth table for an OR is basically if A and B, right, you get a 0. If A or B, you get it on. B or A, and both A and B are on, you get them all on, right? So if they're both the same thing, they'll still match, but in this case, it can be on with either one of these, okay? And then not is the opposite, right? Sometimes called an inverter gate. When you have the combination, it's called a nested gate. So it's not A and B, okay? So here, if A and B were zeros, not A and B is a 1. A and B are not the same, right? So this would have in an AND gate been a 0, but in a NAND gate, it becomes a 1. Same here. And then here, they're both on, but we want to be not on, so we're 0. Okay? NOR is just a nested inclusive, right? So it's going to be the opposite of our OR gate, because now it's not whatever would have been the answer here. Okay? They're not limited to 2 inputs. Theoretically, there's no limit. You can have infinite inputs, and you can keep going down that Boolean logic, right? There were coincidence, exclusive NOR, and exclusive OR. This should be an OR and an OR. Gates in the handbook. So make sure that you've read those. They're the same kinds of things we just went over, okay? And the complex logic devices in the handbook, it also talks about a little bit, so make sure you read that. So we're going to go through a couple of questions about some diagrams on the next few pages, just to make sure we've all got this, okay? So we'll have to, let's see, how did I write this? Go back and forth. Okay, so there's some numbered gates. Okay, 1, 2, 3, 4, 5, 6. What is number 1? What's that symbol for? I think if you pull up the handbook, you're going to guess not? Nor. No. It's an and. Did you pull up the handbook?
Then there's 3 inputs and
So let me pull up the symbology in the handbook for you guys. Okay, so in volume 2 of the Prints and Drawing Handbook, on page 55 of the PDF,
it's volume 2, not volume 1.
correct, volume 2. Right here. $55. What do you guys online think? Number 1 gate. I'll switch back over to the presentation here. Our number 1 gate here. Haley says and. That is correct. It's an and. Okay. What's gate number 2? I'll leave that symbology up. Number 2? Or. Okay. Number 3? Not. Number 4?
Okay, why are we learning this stuff? Not now, but in the other one, they're kind of different. Why are we learning this?
What do you mean they're different?
Like we're learning in the electrical classes, we're learning different symbols, and I just feel like we should be learning our symbols.
What he's saying is last year, the symbols we worked with didn't look like that at all.
I got into it with Mike about this, it's different.
It's those symbols that are, if you scroll.
Like,
What's the
I
point of
would
teaching
ask
us
you,
that stuff if we're gonna come in here with this stuff? You know?
It's
I'm
similar
not
to
saying
those
bad
ones.
about
Similar like this?
this.
Yeah, they're similar to
Yeah.
that.
I just wanna
think
be
that's
learning
what's
this stuff,
frustrating.
if this is what we're gonna be.
because,
So, no, what's hard about
Sorry, I just.
drawings and diagrams? No, it's totally fine. What's hard about drawings and diagrams is this is less of an absolute field, right? There's an intersection here between us STEM people and some people who are artistic, right? The drafters, right? They have to actually draw these things. And so there's a lot of conventions that are allowed, and different fields have slightly different preferences, and they change over time. As Jeremy said, the drawings from 1989 that we went over from ATR have some different symbols and conventions than he uses because he's a more modern person, right? He was not working on drawings in 1989. Okay, so this is a field where you, one, have to be a little bit more fluid. It's not an absolute. It is not absolutely going to be this. Here, I mean, they're telling you that different companies use different standards, right? The International Electrical Engineering Society,
And that's what we learned,
yeah,
is all of those.
okay, yeah, that's what they like to use. And when you took an electronics class, of course you took it from someone who's associated with IEEE and ANSI. That's the governing body for their field, and they're gonna show you that. GE Hitachi builds nuclear power plants. So of course the nuclear industry is gonna say, okay, GE, whatever you drew, we're gonna use it, right? So the DOE handbook is trying to show you a variety of symbols that can be used. Ultimately, what you have to know is that wherever you're getting your drawing from, you need to get their symbology list, right? I am telling you the symbology list we're using is in the DOE handbook because we all have access to that. But even then, you can draw any one of these 7 and tell me the same thing. And if it's not the one I personally have seen a lot, I have to go look up your drawing in the handbook myself, right? That is what it is in drawings. And it's actually one of the reasons that I want to change this class and it's been an entire semester, 4 hours a week from just drawings. Because ultimately what I need to teach you is there's some conventions, you gotta be able to read the flow, you gotta be able to ask your company for their symbology, right? And I think there's a lot more documentation stuff that you guys should be spending time on. And that's part of why our final project is the way it is gonna be. But being frustrated by that is fine. Realizing, you know, this is gonna sound a little rude, it doesn't matter that you're frustrated, it just is different between different disciplines, is the reality. So, yeah, hopefully for those of you online, that explanation of reality kind of helps you see why we have, like, this looks nothing like this, right?
Right, that's what I just.
Yeah. I have only seen these 2 for knots. I've never seen this one used. I have seen the triangle sometimes. So like, if I saw that, I'd have to look that up. I wouldn't necessarily look at a drawing and say, oh, I know exactly what that's supposed to say.
I like the box with the crosses, you know, because then you know, it's not this.
Yeah. Well, and I like this convention for nor, because it takes or and it adds the knot. And this is and it just adds the knot.
all the
Right.
negatives have an X in them. And nor and not have an X in them
Yeah.
somewhere.
And so I really like that way of doing it. I have also been in the nuclear industry my whole life, and GE makes nuclear stuff, so they get to kind of set some of that culture, right? So hopefully, even if it's not a satisfying answer, that tells you why. You don't have to like it, but that is the why. Okay?
Can you go back and start with two?
Can I go what?
Start with two, and then you do that.
Yes.
Ask them that.
What is this one? Four.
How do you know?
So this is a circle going from multiple inputs to one. A circle
Only circle,
going from multiple inputs to one.
and then know which is
So it doesn't matter whether it's 2, 3, or 10
That's what I
inputs,
was wondering.
It's
input.
multiple inputs with one thing coming out?
Because
Is it-
remember,
Okay.
what we just said is that theoretically, there's no limit, right?
Right.
However many inputs we show, the gate can handle as many as we want to show. Usually you won't have a system that has 50, 60, a million inputs, right? That would probably overwhelm your gate on your actual circuit or system. But however many, that we have, we pull back up the DOE. This is just showing us how many are actually in our system. It doesn't matter.
I'm a little behind the curve on these, and I always have been. Why is the and, isn't the and also multiple inputs and one output as well as the or? Is it not? I mean,
Yeah.
and if it is, then how do I tell the difference between and or?
Square
Just
and
pick
round.
the square and the round.
That's right.
Yep.
So much easier to learn it that way than the way that.
Yes.
Yeah, I don't
Everybody was
even-
so
I actually
confusing.
might grasp this by looking at that.
And that's consistent, it looks like.
Yeah. So if we remember that, GE, nuclear company, and we look a little closer to this column than IEEE, because we're not actually EEs or EETs, right? You're gonna see this more often. So the square is an and, the circle is an or, the square is
And,
the square with a X through it is a not,
yeah,
the circle is a or, and the circle is a or.
And again, what the four is, please?
Number 4,
Yeah, and,
and.
okay. And that drawing that your finger's on is conforming to the nuclear standard, so more so.
Yes.
And that's
Now,
what
I say that, you might occasionally find a place that their drafter used to work for an IEEE place, and their drawings at that nuclear power plant are a little different. Like, so understand, when you go to work someplace, and you start looking at their drawings, ask for their symbology. Okay? But in general,
For us and the other for the.
at the 3 plants that I've worked at, so every one at INL, I'll just count that as one, and then the 2 NRC reactors I've been at, this is what I've seen consistently at all of those, so. Does that help you?
Oh, yeah.
Okay.
That's almost like a breakthrough,
Exactly.
perhaps.
And I think that they did this because, like nuclear engineers, I took exactly one electronics class, only one, and it was only a detector electronics. All I had to do, very specific, here's detectors, here's how they work. And so I think that they know that nuclear engineers are kind of dumb when it comes to this stuff, right? So they gave us a very simple way to do it. At least that's what my electrical engineering friends have always told me. Yeah, Kyle.
So, with this logic diagram, we have schematic symbols as well as logic diagrams. So how do you include them and mix them all?
It depends on what we're trying to tell us about the system, right? These are just replacing some of the schematic symbols, right? We know that we're gonna do this through like a relay, right? We know that because we've been trained to know these systems, right? ESET energy systems, like you guys get a lot of systems training. We know that that is what will be here. But right now, in this moment, when we're looking at this drawing, for whatever reason, we're not interested in knowing exactly the component that's put here, just the function. And so they might put, some little signals and control valves, right? Some of these other little things that tells us what's happening. So we kind of know what system we're looking at. But what we're interested in is really just what's happening. Okay, so now that we have, sorry, we didn't do this one because it's not numbered, but this is another, yeah, not. But we've got and, ors, and a not. So what is the function of this, right? Let me pull it back up, okay? This input, okay, signal is on when the hand switch is in the auto position. So is this signal true or false right now? On or off? On. Okay. Do we have a safety signal coming in?
Yeah.
And this gate makes it so it's off. So we've got the signal, we know it's there, but we don't currently have an alarm, right? Okay. This is fully open. Okay, so that's going to be our on, right? So what signal's coming out here?
Well, like nothing, right? It's,
Well, this
It's
is
an-
on,
it's an and gate, right?
right?
And doesn't,
All have to
it,
be on.
they all three have to be on.
Right?
So like, would there be nothing coming out or? Because two of them are on and one's off, right?
Yeah. Two are on, one are off. That came in on,
Yep.
left off, so it needs all three.
Right.
And it only has two, so it's off.
Mhm. So, good. And then here, for this logic, the signal is on when the hand switch is in the open position. Okay? So here, this is on, and we determined that this is off. So what's coming out here?
On.
On, because it's an or. If either one of them is on, it's on. Okay? Signal is on when the switch is in the closed position. So here our signal's on. So what happens here? No signal. So now there's an off and an on. So what's this? Off. Okay? So our flow control valve, right, here is controlled by this solenoid switch, right? That's what it's showing us here. Okay. So when we finally get to here, is our solenoid switch activating or not? No. No. It's not on.
It is. Going crazy.
You what?
Solar ones.
One of the solar ones?
Something.
Yeah, I'm not sure exactly, but so essentially, we don't have this
Flow control valve.
correct. Okay? Any questions? Anybody online?
I have a quick question.
Yes.
Can you see me drawing on the board?
Yes,
Yeah.
we did.
Okay,
Oh.
that's good to know. Good thing I didn't draw anything bad on there.
Kyle was just saying that it's good you didn't. Okay. All right. Hopefully that was some good review and we can end it there.
Alrighty, are we going over anything,